Good day everyone. So this is my topic in activity number 7. First is my chosen topic is Moore encapsulant to silicon via. So first we're gonna discuss Moore law. So Moore law is a term used to refer an observation made by Gordon Moore in 1965 that the number of transistors in a dense integrated circuit doubles every 2 years. So the next is Moore law is observation and projection of historical trend. Rather than a law of physics, it is an empirical relationship linked to gains from experience in production. So the observation is named after Gordon Moore, a co-founder of Fairchild Semiconductor and Intel in 1965, posited a doubling every year in the number of components per integrated circuits, and project this rate of growth would continue for at least another decade. In 1975, looking forward to the next decade, he revised the forecast to doubling every 2 years, a compound annual growth of 41%. While Moore did not use empirical evidence in forecasting that the historical trend would continue, his prediction held since 1975 and became known as a law. More prediction has been used in the semiconductor industry to guide long-term planning and to set targets for research and development, thus functioning some of extent self-fulfilling prophecy. Advancement in digital electronics such as reduction of inequality adjusted microprocessor prices, the increase in memory capacity, the improvement of sensor, and even the number and size of pixels in digital cameras are strongly linked to Moore's law. These step changes in digital electronics have been a driving force of technological and social change, productivity, and economic growth. In industry, experts have not reached a consensus on exactly when Moore's law will cease to supply. Microprocessor architects reports that semiconductor advancement has slowed industry-wide since around 2010. This is the example of Moore law image. Encapsulant. Encapsulants and molding compounds encompass a broad range of material whose primary function is to protect electronic components from detrimental chemical, mechanical, electrical, and thermal environment. Encapsulants and conventionally provided two important functions: optical ray management and mechanical and environmental protection. Epoxy resin has been commonly used. As the emerge of blue and UV LEDs, the discoloring degradation caused by the UV absorption by the aromatic compounds has become a serious issue. High power applications increase heat generation, which promotes the degradation of epoxy resin. In addition, cracking often happens due to the thermal expansion of lead chips. Silicon resin such as gel, rubber, and resin depending on the cured hardness is a common replacement. It is highly transparent and resistant to UV and increased temperature. Silicon is a commonly a softer and less dense material. Early silicon package device encountered failures due to weaker mechanical and environmental protections. For example, is against the moisture. Adhesion is also weak, causing air gaps between lead chips and encapsulant, which lead light extraction to be reduces, and fractive index is generally smaller than epoxy. So, regardless of these weak points, recent progress in material properties has promoted usage of silicon. Die bonding also prefers to use silicon resin rather than the conventional epoxy. In addition, the conventional requirements such as transparency, environmental resistance, and hardness, etc. Recent requirements include high refractive indices and high heat conductivity. Glass materials may be thought as an option, however, lack cost effectiveness and ease of shaping. The curing temperature needs to be lower than common semiconductor processing temperature, which is 400 degrees Celsius and above. Hybrid materials are also researched. Viscosity is another important property of encapsulants upon package information, according to Okuno in 1998. Encapsulant images. Example of this image is the solar panel, which is its part is TSV or through silicon via. Electronic engineering, a through-silicon via or through-chip via, is a vertical electrical connection that passes completely through a silicon wafer or die. TSVs are high-performance interconnect technologies used as an alternative to wire bond and flip chips to create 3D packages and 3D integrated circuits. Compared to the alternatives such as packages and on packages, the interconnect and device density is substantially higher and the length of the connection becomes shorter. A through-silicon via is a type of via connection used in microchips engineering and manufacturing that completely passes through a silicon die or wafer to allow for stacking of silicon dies. TSV is an important component for creating 3D packages and 3D integrated circuits. This type of connection performs better than its alternatives, such as package-on-package, since its density is higher and its connection shorter. Through-silicon via is used creating 3D packages that contain more than one integrated circuit that is vertically stacked in a way that occupies less space while still allowing for greater connectivity. Before STV's 3D package had a stack IC's wires at the edges, which increased the length and width and usually required an additional interposer layer between the ICs, resulting in a much bigger package. This TSV removes the need of edge wiring and interposers, which result into a smaller and flatter package. Three-dimensional ICs are vertically tracked chips similar to a 3D package but act as a single unit, which allow them to pack more functionalities in a relatively small footprint. TSV further enhances this by providing a short, high-speed connection between the different layers. This is the images of through silicon via. So that's all, and thank you.